Okay, so let's look at problem 15. Now in problem 15, all I'm asking you to do is convert that binary pattern of ones and zeros to hexadecimal. This is merely a matter of dividing it into nibbles and representing each one of those nibbles with the hexadecimal pattern. Well, let's go ahead and make a little table over here to the right, which shows for all the different nibble patterns what is our hexadecimal equivalent? And in fact, while we're at it, why don't we figure out what the BCD equivalent is too? Now, with a nibble, remember that's 4 bits, we have 2 to the 4th or 16 possible patterns of ones and zeros. Half of those are going to start with zeros. So I'm going to have 8 zeros and 8 ones. Now, of the next bit position, half of those are going to start with 0, half of them are going to start with 1. So we're going to have 4 zeros and then 4 ones, and then 4 zeros and then 4 ones. The next column is going to be 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, and then the last column is going to be alternating back and forth 0, 1, 0, 1 all the way down. Now I recommend this method because it gives you not only every possible pattern of ones and zeros, but they're in ascending order. So we start out hex 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. And then at 9, we then shift to the letters, right? A, B, C, D, E, F. The reason why I put a line there is because for the BCD column, we have the values in decimal exactly the same as they were for hex. But once you go to the letters, those patterns don't exist in the BCD nibble patterns that you'll do the conversion for. All right. Now that we have our table here with all the different patterns of ones and zeros, we can convert this guy to hexadecimal. Now, one of the biggest errors I see is when people start converting from the left-hand side. Please do not do that. That means that you are assuming that the number of bits we have is exactly divisible by 4. It may be that Tarnoff has created a number that has leading zeros, which he usually does. So, what we're going to do now is divide this into nibbles. So we're going to divide it into groups of 4 starting on the right-hand side. We're going to keep dividing into 4. And that will show us that we actually did have an odd number of bits and requires 3 leading zeros to make that last or most significant nibble, set it properly. Now all we need to do is look for what each one of these nibbles maps to in our binary to hexadecimal table. So 0001, that's this second row right here. That's equivalent to a hexadecimal 1. The next position, 0101, that is a hexadecimal 5. That maps to the 5. Next position, 0100, that maps to 4. 1110, that one comes down to the second to the last line, that's E. 0111, that's 7. 0101, we've already shown that's equal to 5. And then 1010, that's A. So the answer to number 15 is 154E75A. And you can either put the little subscript base 16 or the 0x to indicate the way a programmer would identify a number as hexadecimal. Now, number 16, if you're doing a D2L test, more than likely I'm going to ask you to do just a straight conversion from BCD, from a pattern of ones and zeros in BCD, to the actual decimal number. And that would matter, and all that means is that you would just simply divide, like once again, starting on the right-hand side, divide this number into nibbles, all right? And so it just so happens with this case that it is divisible by 4. The number of bits we've got is divisible by 4. Now we use our table, except this time focusing on the BCD values and represent in anything that's any other of these patterns, the ones that in hex are A through F, are illegal in BCD. Now, if we were to look at this number as a BCD number, This first number is the ones place. The rightmost nibble is the ones place. Then we have the tens place, then the hundreds place, then the thousands place, then the 10,000s place, right? And then the 100,000s place, and then the millions place. All right. And so this number, if it were an appropriate BCD value, this 1001 in the millions place, that means we'd have 9 millions. The 1 in the 100,000s place means we have 100,000s. The next number, 0100, it maps to 4 over in the BCD table, so that means we have 4 10,000s. The thousands place has a 1010 in it, which causes a problem because that's an illegal value. And so that is not a BCD value. So this answer to 16 is false. The 1001 means we have 9 100s. The 0110 means we have 6 10s. And the 1001 means we have 9 1s. But we've already indicated with this illegal position right here that we cannot represent, that this number is not a valid BCD number. All right, one more problem for this video. We talked a little bit about gray code, and gray code, if you recall, is actually not it's a pattern of ones and zeros. It's a sequence of ones and zeros, except the problem is that if we do anything with physical position sensors, something that is trying to send us a binary value back based on a pattern of ones and zeros, we may read those mechanical positions at the, kind of as they're changing. And if we do, and more than one bit is changing, then we might get an erroneous value. So for example, what if our mechanical positions went from 0, 1, 1, 1, that's 7, to 1, 0, 0, 0, numerically that's 8. But what if these 3 bits don't change as quickly as the first bit does, and we read an erroneous value of 1111 in the middle? We just happen to read just at that right instant, or I guess wrong instant. Now, gray code creates sequences of numbers that when you go from element to element to element, only a single bit changes. This number right here is the binary representation of the position we're looking at. So what we're saying is this 000101, that's 5, which what we want to do is figure out, well, what is the 5th position in the gray code sequence? Now, if you remember, there was a process we went through, and the process was this. First of all, you copy down the number of the binary value of the position you're trying to convert to gray code. Then you put a leading 0. This makes it so that we have 6 pairs of neighboring bits. And if the neighboring bits are the same, like in these first 2 bits, they're both 0, you copy down a 0. The next 2 bits are also the same, so you copy down a 0. The next 2 bits are also the same, so you copy down a 0. The next 2 bits are different. One's a 0, one's a 1, so that's a 1 in that position. 1, 0, they're different, so that copies down a 1. 0, 1, they're different, so you copy down a 1. And so the 5th position of the 6-bit binary gray code sequence is 000111. Now, please understand, when I say the 5th position, that is based on an understanding that we're starting at the 0th position. In our next video, we're going to start with the medium-ish answers, a little bit more complicated than the ones we've been working up to now.